Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Dave Stevenson, who's come up to us from Caltech, where he's the Marvin L. Goldberger Professor of Planetary Science. He did a BS at Victoria University of Wellington in New Zealand, and then came across to do his Masters and PhD at Cornell. The topic of his PhD was interior structure of Jupiter, and he studied that with Edwin Salpeter as his advisor. In 1980, he moved across to Caltech, and then after that, he was appointed the Van Osdol Professor. He was the chair of the Division of Geological and Planetary Sciences for a time, and as I mentioned, is now the Goldberger Professor at Caltech. In 1984, he was awarded the Urey Prize of the Division of Planetary Sciences and of the AAAS. And in 1994, the Whipple Award, and in 1998, he received the Hess Medal. He's a fellow of the AGU and the Royal Society of London. The career interests have included Earth and formation, giant planet zonal flows and interior structure of giant planets, planetary interiors and magnetic fields, icy satellites, and also the deep Earth. And today he's going to talk to us about a newer growing interest of exoplanets. So please join me in welcoming Dave.
So thank you for the invitation to speak here today. In the last decade or so, we have seen a spectacular development in science and in our understanding of the universe, and that's the discovery of planets around other stars. And so it has become important to find out what planets might be like. It is already apparent that among these planets there are bodies that could be in some sense like Earth, so far more perhaps like the Earth. And so we have to think about what those bodies might be like in their observable properties and in what goes on inside the planet. So that's the topic I've chosen for today, but in fact you will see as I go along that I'm addressing a broader subject, the subject of planetary structure and how planetary structure gets determined. And so despite the title, you're going to hear things about giant planets, about Uranus and Neptune, as well as bodies like the Earth. But I want to begin with a very simple observation and what comes from that observation. Consider this scene, a very typical scene at Earth's surface. Might not be the South Indian Ocean perhaps, but certainly a very common situation, atmosphere above, ocean below. Think about that. Think about why it is so. The reason why it is so is thermodynamics, not gravity, thermodynamics. For we live on a planet where the conditions are such, where the temperature is such, that these two media phase separate. So the reason why you have an ocean and why you have an atmosphere and why you have a very sharp boundary, the horizon between them, is because water and oil and air unmix below about 600 Kelvin, roughly for the pressures of interest, a similar temperature to the critical temperature for water. The role of gravity in this situation is to set up the order in which these layers exist. Gravity is not the reason why they are separate. This is absolutely fundamental to my entire talk, so it's important for you to understand this. It is thermodynamics that defines the existence of the layers. You might say, well, okay, water is heavier than air. Actually, in terms of molecular weight, that's not true. H2O has a smaller molecular weight than nitrogen or oxygen. But, of course, once thermodynamics says that I have two media that won't mix, then gravity will set in. So gravity determines the ordering of the layers. It does not determine the existence of the layers. Now, there's more to this picture, of course. In the case of Earth's atmosphere and Earth's ocean, we're not dealing with single component systems. The atmosphere is itself a mixture driven by the entropy of mixing among the nitrogen and oxygen molecules primarily. And in the water, we also have a mixture. The salt mixed in with the water. Again, thermodynamics is determining that. So we have both mixing and unmixing taking place in the system. This must be contrasted with another idea of mixtures, such as in this rock. This is a troctolite, comes from the Earth's mantle, beautiful rock. And you can see, of course, by looking at it, that it is a mixture of different minerals. This is a mechanical mixture, fundamentally different from the mixing down to the atomic level that we have in the air in this room, which is driven, of course, by entropy. In this case, the minerals do not want to mix down to the atomic level, but because the material is stiff, it's not behaving as a fluid, it will stay mixed. It will not separate, even over billions of years, even if it is hot. So the mechanical mixture will depend, of course, on the rheology, that is, the material properties of the mixture, as well as the thermodynamics. Perhaps a better example, a more relevant example to planets, is these two materials that you all know and perhaps love, mayonnaise and ice cream. These are mechanical mixtures. They may look smooth, they may look uniform, whereas the rock I showed you did not even look uniform. But these are, of course, mechanical mixtures. If I blow up the mayonnaise, what I see is little globules of fat in a medium that is water-dominated, and of course this is because water and oil don't mix. So this is a mechanical mixture. If you made a planet out of ice cream or out of mayonnaise and let it sit there for geologic time, it would actually separate. If you buy cheap ice cream at the local supermarket and leave it in your freezer for 6 months, maybe you've tried this experiment, you'll know what happens. It does actually start to phase separate. So planets, given time, given the action of gravity, and given the large length scales, will eventually separate if the thermodynamics says at the outset that they want to. So this is a lead-in to a very basic question in planetary science, which is whether a planet has a core. There are two end-member stories for why a planet may have a core. At the top, we see the bottom-up story. The bottom-up story is where you build a core made of some material and then place on top of that a different kind of material. So that would be an accretion of a different composition on top. And then at the bottom of the figure, we have the top-down story. The top-down story would be like building a planet out of ice cream or mayonnaise. Let it sit there, let it cook. It will separate. Thermodynamics drives the separation. Gravity then acts on what the thermodynamics says you want to do and produces the differentiated structure. And in our solar system, we have, we think, examples of both kinds of core formation processes. The bottom up, we think, is the way planets like Jupiter form. So that you build a core that may be rock, perhaps ice as well, and then you put gas on top. Whereas for the terrestrial planets, where we actually have better understanding because we can use the information we get from geochemistry and from elemental partitioning experiments, we think that Earth's core is a top-down process, that you built the planet as an emulsion, if you will, just like mayonnaise or ice cream, and then separated out the components because they are immiscible. Now, this is actually central to my entire seminar, because the figure at the top that we think is applicable to giant planets is an instance where the material that is in the core is actually able to dissolve in the material above, and only persists because if you build that structure at time 0, it can take longer than the age of the solar system to mix the material up, even assuming that you have enough energy. So in the case of Earth's core, we have cartoons for how core formation takes place. In fact, we think you do make an emulsion. This diagram shows essentially an emulsion, a magma ocean with droplets of iron whose size is determined by surface tension, so it's the same physics that determines raindrops in the Earth's atmosphere, and then that material perhaps macro-segregates and finds its way to the core, all of this happening very early in Earth history, in the first 100 million years, perhaps even less, during the actual accretion process. The story for Earth may actually be more complicated, because we think that in the process of making the Earth, there were giant impacts. And so instead of material just gently raining down, like rain falling from clouds in the Earth's atmosphere, the process is very traumatic. It involves events that release an enormous amount of energy and deliver an enormous amount of material all at once, like a body, perhaps the mass of Mars, hitting the Earth. And in that case, the details are different. It may not be a raindrop formation process. It may be large blobs that are not fully equilibrated thermodynamically, finding their way to the core. This is still imperfectly understood. In the case of giant planets, we have two different things to think about. One is the process of immiscibility, just as with water and oil not wanting to mix. Hydrogen and helium mix imperfectly so that helium can rain down towards the center. But at the same time, that thing in the center that is of great interest, the rocky core, the thing that we're hoping to understand with a billion-dollar mission that's currently on its way to Jupiter, Juno, is in fact a product of the history of the planet, and is only there by virtue of having been put there in the first place, and not because it wants to be there. It actually wants to dissolve in the material above. How do we know that? We know that from quantum mechanical calculations. This is wonderful work done by Burkhard Militzer at Berkeley and his postdoc, Hugh Wilson. And what they have done is calculate the thermodynamics of this system. The details are not important. The important point here is that they find that the materials that are in the core of Jupiter want to dissolve in the hydrogen above. The hydrogen above is in a metallic state. It's a liquid metal. And these materials, MgO and water, happily dissolve because the temperatures are very high. Temperatures always help because the entropy of mixing is what drives this solution process. And so one has, in the planets of our solar system, a range of situations, ranging from cases where things would like to be mixed to cases where things are imperfectly mixed. Here are some cartoons showing cross-sections for the giant planets from the work of Tristan Guyot. And the details are not important, but I want you to notice that in the case of Uranus and Neptune, there is this uncertainty about the extent to which the materials are mixed. And this is going to be an important part of the story I want to get across to you today, because Uranus and Neptune are in some sense going along a sequence of planetary structures that will end up at objects that are like super-Earths, with or without water. And in the case of a body like Uranus, one has this dilemma, this uncertainty that we still have about the internal structure. This is a body whose temperature is very low in the atmosphere, 50 Kelvin, 60 Kelvin, but inside is at thousands of degrees. And under those conditions, the water, the hydrogen, and the rock can all mix down to the atomic level. And as a consequence, the structure is uncertain. You cannot think of it as a simple layered structure as with the cartoon at the top. It's something that is intermediate between being layered like an onion and being completely mixed. Now, what does all this have to do with exoplanets? Well, I have to show the obligatory diagram, which of course is always out of date unless you update it the night before. So this is radius versus mass, based mainly on Kepler data and follow-up to give you the masses. Kepler, of course, gives you radii, albeit with some uncertainty because of the uncertainty of the star and just from the data itself. And of course, in such a diagram where you plot radius versus mass, you can compare the observed values with various composition planets. And so you see these various lines of different colors, ranging from compositions that might be pure water out down to compositions that are pure iron. And of course, this is a selected diagram. You can go to higher masses, you can go to larger radii. We know that there are many bodies that are not in this diagram. Hot Jupiters, for example, which have radii that are more than 10 times the radius of the Earth. In fact, 15 or so times the radius of the Earth. An important message that I want to put across to you is that the introductory comments I made to you about whether or not planets are layered is not particularly relevant to understanding a diagram like this, because it actually doesn't matter all that much. A big chunk of ice cream is going to occupy the same volume, irrespective of whether I separate the oil from water components as an ice cream or mayonnaise, or whether I keep it well mixed. It doesn't make much difference for radius as a function of mass. But if you want to go beyond that and talk about how the planet actually works, what its atmosphere is going to be like, how it formed, how it evolved, you have to go to the next step and think about whether or not it is layered or whether or not it is mixed. And that is a central idea in this talk. So why do we care about this question? Why does it matter whether a planet has well-defined layers? And the answer is that almost all of the properties, except this one that we've measured so far, which is radius as a function of mass, depend on this. The nature of the atmosphere is going to depend on what's inside. Make no mistake about it. The air in this room is a consequence of an evolution of a planet that was layered. It makes a difference. The existence of an ocean, obviously. The question of whether you have plate tectonics and mantle convection depends crucially on your understanding of whether a planet separates into layers or stays well mixed. Whether or not it has a magnetic field depends on whether there's a core. There's a lot of papers out there making speculations about whether exoplanets have magnetic fields. In my opinion, most of that work is worthless because the people doing it haven't asked the fundamental question. You have to first ask whether the planet has a core before you ask the nature of the convection or absence of convection in that core. And of course, obviously, to the extent that these things affect the origin of life, the question of life on these planets is also affected by the question of whether the planet is layered. It is also true that if you want to build a story that tells you how the planet formed and how it evolved, you have to understand whether or not the planet is layered. So all of this has been introduction. And I now turn to some specific questions. The first of which is going to make a tie to observations, but then extrapolate to SuperEarths. And that first topic is going to be an attempt to explain a current problem with Earth's core. For it turns out that we have difficulty with the standard ideas, difficulty understanding why Earth has a magnetic field for most of Earth history. That's an observational fact. The Earth has had a magnetic field for most of its history. It's expressed in the rocks through paleomagnetic record. And I'm going to describe an answer to that question that has to do with the imperfect layering of the Earth, and then extrapolate from that to say something about what happens in SuperEarths, and argue, in fact, that SuperEarths do not have cores in the way we normally talk about a core. I'm going to talk briefly about whether or not Uranus has an ocean, and then I'm going to talk at the end about this general question of how special the Earth is, because I'm going to argue that the Earth is actually rather special in multiple ways. We are, in some sense, an intermediate planet, not too big, not too small, and many other planets will be different from us, a lot more water, perhaps even in some cases less water, and so we are, in fact, somewhat special. But let's deal now first with this very interesting puzzle that has concerned a lot of us in the geophysics community for the last couple of years, and that is, how can it be that the Earth keeps maintaining a magnetic field for billions of years? The process by which that field is maintained is, we think, well understood. It is called a dynamo. The dynamo requires convective motions in a liquid that is electrically conducting. The Earth's core is unquestionably a liquid, for the most part, has a solid central region, but that's only 5% of the volume. It is electrically conducting. It is mostly iron. Question is whether it will convect in the appropriate manner for billions of years. And there's a problem. The problem that has emerged in just the last couple of years is that we have new estimates for the electrical and thermal conductivities of the core. Now, you might think that having a high electrical conductivity is a good thing for maintaining a magnetic field. Not true. High electrical conductivity also means high thermal conductivity. That's always true with metals. It's called the Wiedemann-Franz law. And it's because electrons do double duty. They carry electrical current, but they also carry heat. And if you have high thermal conductivity, that can turn off the convection. So that's the puzzle. Now, the standard solution to this puzzle is in part to invoke Earth's inner core. For indeed, the centermost part of the Earth is solid, it's frozen. It's the hottest part of Earth, but it's also frozen. It's at about 6,000 Kelvin. And as that inner core grows, it excludes light elements, at least in part, and those light elements then drive the convection and keep the dynamo going. But there's a problem with that, and the problem is that it only works for about 1 billion years. So this just summarizes the idea that if you have high conductivity, you also have high heat flow, and this is a problem if you want to keep the core convecting for billions of years. We think, in fact, that Earth's inner core is young. It's less than about 1 billion years old. And so it looks as though you need alternative energy sources. You could put more radioactivity in the core. You could say that the Earth started out very hot. You could do some other kind of mixing process stirring the core. Or you could have some non-standard evolution, and that, in fact, is what I'm going to invoke. Putting in more radioactivity is not supported by experiment. There is no evidence that uranium, thorium, or potassium will go into Earth's core under the oxidation states that are relevant for Earth's core. If you try and make a model where the Earth starts out hot, what you find is that the Earth cools very quickly, and cools to a state where it is no longer cooling quickly, and that also doesn't work. Equivalently, an equivalent statement to that is that if you integrate back in time Earth's thermal history and insist that it's cooling rapidly, then you get what's called a thermal catastrophe. You get a runaway, temperatures rise to much higher than acceptable values in less than the age of the Earth. There is no precessional or tidal process that is anywhere near adequate for stirring Earth's core. And so it seems as though we are indeed forced to a non-standard evolution, which is chemical. That is to say, instead of the usual picture of the Earth's core and the Earth's mantle being completely separate systems, that there is a chemical interaction between them. And this arises naturally because the mantle materials have finite solubility in the core. So my solution to the Earth's core problem is X solution. X solution means that as Earth's core cools, material will exsolve. Just think of it as snow that rains upwards because it's lighter than the iron from which it comes, and that material will come up and underplate the mantle. This is a natural outcome of forming the Earth and the Moon through one or more giant impacts, because that creates the high temperature state in which you can mix material from the mantle into the core. And when I use the word mix in this context, I mean down to the atomic level. I don't mean mixing in the mechanical sense like mayonnaise or ice cream. I mean a true alloy. This process is actually 10 times more effective per unit mass exsolved than growing the inner core, because the material that's coming out of the core is a factor of 2 different in density, whereas the difference between the inner and outer core densities is only 10%. This is very effective in Earth history, which is early Earth history, which is the best time to use this process, and it's actually supported by mineral physics data. So my core recipe, my recipe for the Earth, is to put into the Earth's core a mixture of 2 components. The biggest one is the standard one that the geochemists love. Geochemists have worked on this for decades. They've developed highly elaborate models for the partitioning of elements between the core and the mantle. And this is a low temperature, low pressure, equilibrated material. Low temperature doesn't mean that low, by the way. It's more like 3,000 or 4,000 Kelvin. And then you mix in a small component, which is a high temperature component that has mantle material as part of it. The low temperature stuff is needed as the predominant component to explain what we know from seismology for the mean density, what we infer for temperatures, what we infer for the hydrophile abundance patterns of the observed mantle. And the high temperature stuff adds a sprinkling of lithophiles. Lithophiles are the elements that we normally think of as not being naturally resident in the core, such as magnesium. And they will subsequently come out. They don't want to be dissolved in the core when the core cools. And so as the Earth's core cools over geologic time, that material comes back out and comes to the base of the mantle. The mineral physics data that supports this picture is not yet published. It is the work of Nomura, who's a student with Hiroshi at Tokyo Tech, and they have done diamond cell experiments. And what is shown in this diagram, vertical axis is the amount of material that dissolves in the core, horizontal axis is temperature, and what is shown in this diagram is that when you go to high temperatures, you start to get magnesium, that's the green line, going into the core. So the usual picture of the core and the mantle being well-separated components starts to break down at high temperatures. And if you take those data, and I have, and analyze it by a thermodynamic model, you predict that Earth's core and Earth's mantle will mix completely down to the atomic level at a temperature of 11,600 and above. That, of course, is a much higher temperature than in the present Earth, but that's already an indicator of something very interesting for when you think about super-Earths, because super-Earths will be hotter than Earth inside, and so the core and the mantle will not be well-separated entities. in the current Earth, the core mantle boundary temperature is such that the amount of magnesium that is in the core is quite small. If, however, you go to the ancient core mantle boundary temperatures, the early Earth, you see that there's a lot more magnesium, as well as other things as well. But magnesium is the important driver because it's very abundant. There's also a lot of silicon. That's not new. We've known for quite some time that there's a lot of silicon in the core. So the physical picture that I'm advocating for Earth's core compares two different situations. On the left, the growth of Earth's inner core. On the right, the growth of a layer by exsolution at the base of the Earth's mantle. And these two structures that I show here are equivalent in terms of gravitational energy. If you choose, for example, a layer that is about 10 kilometers thick for the silicates and oxides that come out of the core. So in this picture, the 12-20 kilometer inner core of the Earth, which is only 5% of the Earth's volume, is gravitationally equivalent in terms of its ability to drive the dynamo as a mere 10 kilometers, only 10 kilometers of material that underplates the Earth's mantle. And so this can solve the problem of the Earth's core. Okay, well, I promised you that I would talk about super-Earths, so now let's talk about super-Earths. First point, very important. Gravitational energy rules the world. That's already true for the Earth. People often talk about radioactivity. They talk about the role of radioactivity in driving convection inside the Earth, driving plate tectonics, being so important for geothermal heat flow. It's actually not true. Less than 1/2 of the heat coming through the Earth's surface right now is due to radioactivity. More than 1/2 is, we think, due to the fact that the Earth is cooling. So this is an application of the first law of thermodynamics. But the reason why the Earth is cooling is because there was an enormous amount of energy put into the Earth when it formed. And that energy is gravitational. If you take dispersed matter and bring it in to form an object like the Earth, you get a huge amount of energy released. It's 10 times more than the total energy released by radioactive decay over Earth history. And of course, if I go to a super-Earth, the scaling is such that the gravitational energy becomes even more important. As a consequence, it is not correct to do what people have been doing in the field, which is they take somebody's computer model of an Earth-like planet and they just tune the parameters. They say, okay, I'm going to make an object 2, 3, 4, 5 times the mass of the Earth, and I'm just going to imagine that the core and the mantle will scale up. They put in better equations of state and so on and so forth, but they treat it as if it were a scale model of the Earth, and I think that's actually incorrect. Remember what I said earlier, this is not important for the radius-mass relationship because the question of whether it's mixed or unmixed is not important for radius, not important for mean density, but it is important for everything else. Temperature is actually more important than you might suppose. Planets are degenerate. That word has a precise meaning. It means the electrons are, for the most part, in the ground state. And so you might wonder why temperature matters, but actually it does. It closes off mobility gaps. It takes materials that would normally be semiconducting and makes them into conducting materials, which is what happens if you heat the silicates enough. And of course, importantly for my story, the low pressure part of the system, the atmosphere, depends on the chemical state of what's beneath. Just as it's true as that the air in this room depends on the chemical state down below. The speciation of carbon, the fact that you have CO2 rather than methane, depends on the oxidation state, and it will change if you don't form a core. You drive the system more towards having methane instead of CO2. So here are some important numbers. The energy of Earth formation expressed as a temperature rise is 40,000 Kelvin. That's the quantitative backing for my statement that gravity rules the world. And the energy of Earth formation, Earth mass m, radius r, big G, Newton's gravitational constant, the energy per unit mass divided by the latent heat to vaporize rock is of order unity for the Earth. The Earth is special. Interesting. The Earth is just the right size so that the total energy of formation is enough to vaporize everything. And of course, that doesn't actually happen because sigma t to the fourth radiation is so efficient in cooling the system. But in sudden events like giant impacts, you get very high temperatures. And of course, the gravitational energy is 10 times the total energy released by radioactivity over the history of the system. These are the numbers for the Earth. When you go to super-Earths, the importance of gravity goes up, and the temperatures become larger, partly just because the impact velocities are higher, but also because of adiabatic heating, just the role of pressure in increasing temperatures. So that leads to the following concept. In this diagram, we have mass increasing from the bottom to the top, and we can ask what form the planet will take. If the planet is very low in mass, there may not be enough energy to separate the components that want to be separated. The planet is too cold to even form a core. It's not clear whether this is relevant in our solar system because we have another heat source called aluminum-26 early in the history of the solar system, and so small bodies that formed at that time actually did form cores. And then there's an intermediate range in which the Earth resides. And then as you go to high enough mass, the planets will be too hot to form a core. And so conceptually, this is like a two-component phase diagram, the same diagram you would use for water and oil, or for hydrogen and helium, or whatever. And in this diagram, temperature on the vertical axis, composition on the horizontal axis. This, of course, is a conceptual phase diagram. The mantle's not a single component, the core's not a single component, but it gets across the idea that you have a miscibility gap. This is a very standard phase diagram for systems like water and oil that will phase separate. And I think the temperature that corresponds to the maximum of this curve, based on my calculations, is about 12,000 Kelvin at 1 megabar for the mantle core system. And so what happens when you build a planet is that if you start at very high temperatures, as you would for a very massive planet, and cool it, you cool into the phase-excluded region, you start to make two components, but they're neither mantle nor core the way we normally define them, because that only works if you're way down low on this diagram. Instead, you have something that's vaguely core-like, something that's vaguely mantle-like, and you actually get a compositional gradient. You do not get the sharp boundary that we have between the core and the mantle of the Earth, so sharp that you can scatter seismic waves off it. It will not be like that. And so in terms of the structure of the planet, you may have something that you could say in quotation marks as a core, but it's not like Earth's core because it's got a lot of mantle material in it, much more so than the Earth's core, and then a compositional gradient in which convection is inhibited, and then a mantle which is not like Earth's mantle because it's got metallic iron in it, and it's probably a conductor, and then over the top of that, perhaps a dense steam atmosphere, which will be hot because of the greenhouse effect. So that's the super-Earth story, but it is actually related in an interesting way to a question that arises when talking about Uranus and Neptune. For in my mind, there isn't a sharp boundary. You might have been taught to think of planets in very sharply defined categories, but that's not correct. Because I can think of Uranus and Neptune as being a natural pair of members on a trend of planetary composition that starts with Earth-like bodies, adds water, and then adds just a little bit of gas, like 10% by mass. Uranus and Neptune are actually of great interest for understanding our own solar system. They may actually tell us about the thing that we are striving to understand at the center of Jupiter. They are the naked Jupiter and Saturn cores, perhaps. We don't fully understand how they formed. And of course, as I pointed out earlier, there is this question of how the materials are mixed or unmixed in their interior. Question of whether there's an ocean in Uranus or Neptune. It's even better to think about a water ocean in Neptune. That's an idea that's been around for a long time. It's an unresolved question. And of course, it fits with the general question of whether or not you would have a water ocean on a super-Earth. If we are to talk about whether you have an ocean, we need to decide what it means to have an ocean. And that brings us back to my very first slide in the talk, because it's a thermodynamic question. And so shown here are two diagrams which are the same thermodynamic diagram in which there's a phase-excluded region. That curve has a region within it that is phase-excluded. Phase-excluded means that if you try and occupy that point in phase space, it will spontaneously separate, just like water and oil spontaneously separate, or water and hydrogen normally. And so what will happen in a planet, for example, in the normal picture of Uranus, is that if this is water mole fraction, you form clouds, the cumulus clouds, so there's a convective region, and then you go into a well-mixed interior region. But if you had an ocean, you would jump to a much higher molecular weight material, and it would be a phase transition, a discontinuity in composition, just as the horizon that you saw in my very first slide is a discontinuity going from atmosphere like the atmosphere in this room to something that's mostly water. How do we answer this question? And the answer lies in, of course, thermodynamic data, because thermodynamics lies at the heart of all of these questions. So here is a new result that was published relatively recently, Bali et al., a group in Germany, where they actually measured the critical temperature for mixing of hydrogen and water. And this was a very interesting result because it shows a critical line, which is this dashed red line, that climbs almost linearly, or perhaps even faster than linear with temperature as you go up in pressure. And this line is telling you that if you try to take a mixture of hydrogen and water, it will phase separate if you're below that line and will be fully mixed above that line. Motivation of these people was actually Earth's mantle, which is why you've got these various points about the Archean geotherm and so forth. But this is data of vital importance for understanding Uranus and Neptune. And whoops, what happened? Well, this has never happened to me before, at least not on this computer, but we'll get back. I don't know why that. So what you do is you take this thermodynamic information and place on top of it the temperature profile that would be appropriate to Uranus, Uranus adiabat. And what you discover is it crosses the critical curve twice. And the low pressure crossing corresponds to our usual idea of water clouds, and the high pressure crossing corresponds to an ocean. So these new data tell us, in fact, that Uranus and Neptune have an ocean. So the conclusions for Uranus and Neptune is that these bodies have structures distinctively different. This, by the way, is not true for Jupiter and Saturn, because Jupiter and Saturn have a very different ratio of total water to total hydrogen. I think also that this is relevant for understanding why Uranus and Neptune have distinctively different magnetic fields. They have deep-seated oceans that begin at 2 to 4 GPa, about 1,000 kilometers below the cloud deck. And this is, to me, an exciting development because it removes some of the ambiguity of interior models. But of course, these ideas will also apply to SuperEarths to the extent that we're thinking about models, bodies that may have oceans. The question of whether the ocean will remain as an ocean or mix with the atmosphere, that will depend in part on temperature and in part on pressure. So I'm coming towards the end of my talk, and I want now to give you a little bit of philosophy that lies behind a statement I said earlier that I hope was a little bit provocative, and that is the idea that Earth is actually rather special. For indeed, I think Earth is rather special. I've pointed out already an important sense in which it is special. It is neither too big nor too small. It is big enough that you can have the separation of core from mantle and all the consequences that follow from that in terms of magnetic field and plate tectonics and so forth. But if you made the Earth significantly bigger, it would be a very different beast, because the temperatures and pressures would then be such that you don't separate core from mantle, and you will not have a structure that is at all like Earth. If you make an object that's much smaller, it becomes a lot less interesting. It's less able to hold on to an atmosphere. Perhaps even if it is small enough and does not have aluminum-26 heating, it would not separate core from mantle for a different reason, that you didn't have enough energy. So in the Goldilocks sense that people often like to think about these things, the Earth is special in terms of its mass, not too big, not too small. But it's also special in terms of the amount of water, because the Earth has a coincidence. I think it's a coincidence, and that is the coincidence that the depth of water in Earth's oceans is similar to the height of mountains. Now think about that. These are two things that have nothing to do with each other. There have been suggestions about feedbacks, and there are feedbacks that work in a limited sense. Jim Casting and others have suggested this in terms of the thermodynamics of water at mid-ocean ridges. But in fact, even if what those people are saying is correct, it works in only a limited range. And so we actually are living on a planet that is unusual. It's a planet that has both dry land and ocean. And that, I would argue, is unusual. You could, of course, go to substantially less water, and then you can talk about lakes or whatever, sort of like Titan. But if you look at the entire range of possibilities, the Earth is special. The physics that determines the height of mountains is, to a large extent, disconnected from what goes into determining the depth of the ocean. So, again, we have a Goldilocks situation. Not too much water, not too little. It's not clear, by the way, in terms of habitability, whether having a really deep ocean is a good thing. This may well be an accident of solar system evolution, and it's an open question as to whether that accident is to be found in a similar form for exoplanets. By accident, I mean the particular set of circumstances that occurred in our solar system that allowed for the delivery of a small amount of water to the Earth, but not a lot of water, in the form of ordinary chondrites and some carbonaceous chondritic material. We are also in a situation of having an atmosphere that is not too much or not too little. This again would seem to be, to some extent, an accident. To be sure, there are feedbacks that work here. If you try and draw down the atmosphere a lot so that the Earth cools, then volcanism can replenish it, and so you can rebuild an atmosphere feedbacks will allow you to do that. But in terms of the hydrogen and how much hydrogen you've got, to some extent that is an accident of timing, unless you can persuade yourself that it is always the case that when you're building these super-Earths, you will do so on a timescale so long that you have lost your nebula to the interstellar medium. In our solar system, the argument goes that building a planet like the Earth takes tens of millions of years, and that is supported by the isotopic evidence. And of course, we only retained our hydrogen-rich nebula for at most about 3 million years. But again, it would seem in the full range of all possibilities that this could, to some extent, be an accident of timing. A hydrogen atmosphere can be lost using the UV from the early history of the star. It goes back to the work of Hayashi and his group in 1970s and 80s, where they worried about the possibility that the Earth would have a dense hydrogen atmosphere. So you can lose it, but there's still some interesting accidents of timing that seem to apply there. Now, in all likelihood, you've all heard of this Goldilocks scenario when people talk about the habitable zone, in large part attributable to the ideas of Jim Casting. I confess to never liking that, because I think of habitability in a broader sense, and so I see habitable environments all over the place, almost everywhere except in the center of stars. You can have liquid water all over the place. You can have liquid water inside Pluto. And so I don't see a problem there. But I think to the extent that people are obsessed with this question of Earth-like planets, there is a Goldilocks situation, not in the sense that Jim Casting meant of the habitable zone, but in the broader sense of all of the particular accidents that lead to a particular amount of water and a particular mass and so forth. Enough of the philosophy, and I've come to the end. My final thoughts are these: that we must stop thinking about simple layer cakes. There is this long-standing idea that you can think about planets as being nice layer cakes. It's not correct. Planets evolve compositionally in a way that is dictated by the thermodynamics of immiscibility, partial mixing and miscibility, and of course fluid dynamics, an aspect that I have not emphasized here, but which is actually very important for what goes on in the Earth's oceans and in some stars, a process called double diffusive convection. We are in an exciting era, and it is going to be very difficult to figure out what's going on in exoplanets. But I hope I've given you a feeling for some of the interesting challenges that we have ahead. Thank you.
I see a couple of questions. I get the privilege of asking the first, though, Dave. We know that comets didn't deliver the water to us. So is it possible that the chondrites that you speak of that could have been the source of our water, wouldn't that be present around any similar star in the region where Earth is now, and a super-Earth could, or a planet similar in size to the Earth, could get the same water budget if it's sourced locally in the solar system?
Yes, it's possible, but I can think of 100 other things that are possible as well, some of which would deliver a great deal more water. Planetary migration allows you to bring bodies in from the region that had half water, half ice. What happened in the system derived out of that kind of terrestrial zone. Could you imagine situations where you could get a lot more? Could you imagine situations where it's a lot drier? Maybe. If you did not have the particular architecture that our solar system has, which has delivered materials from the asteroid belt somewhat efficiently, involves the location of Jupiter and the existence of an asteroid belt in the form that we have it. To me, the central message is diversity. There are so many different possibilities. And so, yes, you can certainly think of a situation like the solar system, but I would argue you can think of 100 others that are not.
Okay, I'm going to take my privilege far too far here and ask a question about planet. would you rather water?
It's a toss-up. Jack.
Very nice, Dave. I got a bunch of questions, but the one I'm going to ask is the ocean interface with the atmosphere on Neptune.
Yeah.
What's below, what's above, what's changing substantially in terms of composition and state?
So I do not have a complete answer to that yet. It's something I'm working on. And I'm also limited by the data. There are data that can be used at the low pressure end. Chemical physicists on this for and you have this absolutely sure. There will be method. This will put that into but now I think it one these issues of what the relative abundances of various molecules in the atmosphere. But hopefully as I'm
Kepler 20. Kepler 22 between the size of Neptune.
Yeah.
What from the size of Neptune?
I and other people would draw diagrams like this just for the solar system. And on those diagrams, we would put objects like Uranus and Neptune. And of course, we knew when we played that game that there was no possible way of deciding what Uranus and Neptune were just by looking at radius and mass. And that, I would say, is the message for the Kepler bodies as well. If you are near this boundary, then you can be confident in determining composition because there's nothing that's cosmochemically sensible. You're not going to make a planet out of uranium. There's nothing that cosmochemically sensible that will place you below that dive. Anything above, in principle, is possible and ambiguous. Because if the body is hot, and the Kepler bodies usually are, because you're looking at bodies that are close to the star. If the body is hot, then you have an uncertain mixture. I can take a mixture of gas and rock this is something I pointed out a long time ago, and give you a material that looks like ice in terms of its density. And so if this is the information you have no way of deciding. Now, it's not, so I can't answer your question, but I can tell you where to go. The way you solve this problem is by understanding the atmosphere. And that is something we can do, kind of work that Heva Knudsen and others do, where they do an infrared study of the atmosphere and try and find spectral lines. Now, sometimes these bodies have clouds, and so spectra are boring. That's unfortunate. And so it's even going to be hard with infrared data. But from secondary eclipse data, you have at least the hope of learning something about what's in the atmosphere. And in that way, you can decide, for example, whether it's a planet where you have mixed a huge amount of water into the atmosphere or not, things like that. Or even whether you've mixed the rock in, because some of these bodies are hot enough that the consequences of that will show up in elements that have large opacity, like the alkali metals. So that's the future object. Don't try and do it. They look like this and they try and infer composition. I think that you can't do that except when you're at the extremes, and so you have to do something else, and that's part of the advocacy that I've given you in my talk.
Hello. I am not a professional scientist, so this may come across as a silly question, but earlier you had a chart on and it had emulsified objects, cores, and then non-differentiated planets as a function of the mass. You mentioned, I think I heard you mention a possible heat source that existed in the universe that doesn't exist now.
Yes.
And I was wondering what you were referring to.
Aluminum 26.
Aluminum 26.
The heat source that was produced in a period, well, actually, it's all the time. Being produced in the neighborhood at the time the solar system was formed. It's even been suggested that supernovae are involved. It's probably not supernovae, but one of the things that I think is of great interest for understanding formation of planetary systems is the extent to which the formation process is very traumatic from the point of view of popping slow mass forming as well. The massive stars, of course, evolve very, very fast, and so there are high energy events. There's a suspicion, for example, when you look at some of Mike Brown's work where he studies the Kuiper Belt, objects like Sedna might be telling us that our solar system was disturbed. And that's a natural enough thing if there were stars nearby. Not necessarily companions. A lot of stars, of course, have companions, but stars that were just wandering by, gravitationally disturbing us. And so, but to come back to the point of your question, why am I telling you all these other things? I'm telling you these other things because the question of how much radioactive heating you have, whether you have aluminum 26 in a particular abundance, is on stochastics, on chance circumstances when the system formed. I could have given you a whole different set of topics that are related to the question of what the radioactive heat content would be of planets. I think that's actually secondary, but there's no reason to think that the particular amounts of potassium, uranium, and thorium that we have in the year are special. They vary by quite a lot. They vary by galactic evolution. Likewise, aluminum 26, which is a special case because it decays quickly, will vary quite a lot in the amount that you bring into a system when the planets are forming.
David, over here. Is there any message in the major difference in internal heat sources between Uranus and Neptune, with Uranus very low, that helps you understand the interior?
Yes. This is something I've thought about a lot, and I'm not sure I know the answer. There are 2 points made here. It does actually make a difference closer to the sun. When you bring a planet closer to the star, and it wants to get a temperature that's very much different than the temperature that had no internal heat source, which is true for Uranus, then you get an effect. The planet is able to heat because of the absorbed sunlight. So that's a factor, but it's not enough. We know that the inside of Uranus, the inside of Neptune is different. It looks as if one possible story is that Neptune is more mixed up relative to Uranus. So neither of them are fully mixed, but Neptune is more mixed. How could you do that? I will give you one speculation, that these planets suffered giant impacts. And the giant impacts involve bodies of order the mass of Earth hitting these planets. This actually goes back to Al Cameron, although he never said what I'm about to say, but it's related to things that Al Cameron said. In that story, the fact that Uranus is tipped on its side and imperfectly mixed and therefore has poor heat flow is a consequence of an oblique impact. And a similar impact, but not oblique, would have changed the obliquity of Neptune less, but would have caused more internal stirring. So that's a way of having 2 planets that end up being very different in terms of heat flow, purely because of how they formed.
Hi, Dave. Everything in it have mission.
I'm like a kid in the store. I don't know how to make up my mind. I'm a big fan of Venus, actually. I think you are too. I would love Venus. All 50 of us. But actually, I like Uranus or Neptune. It's a toss-up. Currently, in terms of celestial mechanics, Uranus is a little bit easier. Having a probe would be great, but perhaps we could be cleverer and do it in other ways. You know, in the decadal survey, which I participated in, Uranus got into it as one of the priorities, mainly because of Hubbard. We lobbied for it. I made the argument that Neptune is important. What happened being about Jupiter. In terms of answering that. So if you put and say I have to choose one, I will go for Uranus.
Hello. So in our solar system, we have 2 examples of roughly Earth-sized planets. One has had catastrophic heat that we know of, and one has not. And then we have the 2 Neptune-ish sized planets that are different, maybe, as you say, from their histories, but I think at least on some level more alike than Earth and Venus. And I was wondering if you thought that as you go up the scale from like Earth to Neptune mass, when is it still possible to have like Earth-ish kind of things and Venus-ish kind of things until you get to Neptune-ish and Uranus kind of things, or is it there's something in between like Earth and Neptune that's completely like neither one?
I don't like labels because I think it's continuum. But I often say planets in our solar kind. This is a body that's high to the Earth. With having, I would have thought, it is sort of Neptune. Under the atmosphere. You've got I have this.
Dedicated. How
Neptune. Clouds. Seeing spectra that are telling us that there's clouds.
So I'm curious what you have to say about Mars, which is about a tenth of an Earth mass. I always assumed because it had a higher surface to volume ratio that it was basically just a colder version of the Earth. So, you know, without an inner, you know, with a no outer core, and, you know, it's solid and plate tectonics has stopped, you know, and but it's layered like the Earth. Is what you have to say put that in doubt?
No. My talk was driven in significant part that up until the present, Kepler data sets, a number of instances more massive. As you go to masses less than the Earth, in some sense it becomes better understood what's going on. I would say about Mars that in all likelihood the core is liquid. And so the interesting question for Mars, which is relevant to what I said for the Earth, is how you understand why it has no magnetic field. And presumably means that the core is not convecting. And I can come up with half a dozen stories for why that might be so. But there is an interesting set of questions there that, in the case of the Earth, in comparison with Mars, may be telling us about the range of possible outcomes. By the way, it is not actually correct to assume that the inside of Mars is colder than Earth at the same pressure. Got to compare it, same pressure. This is a point that people often misunderstand. Earth is special because it has plate tectonics. I could have talked about that. Of course, we don't really understand plate tectonics. But one thing we know about plate tectonics is that it's an efficient means of cooling a planet. And so the Earth is actually running colder, properly scaled. You have to think about pressure. As pressure comes in. But appropriately scaled, Earth is running colder than a planet without plate tectonics. Mars does not have plate tectonics. It's in what's called stagnant lid regime. And so the temperatures in the mantle of Mars, if you compare them at the same pressure, might even be higher than for Earth.
And for Venus too, I guess.
And for Venus too. Now Venus, there's a whole other set of questions about Venus, which have to do with whether there was some change in the character of convection over geologic time. Some people have talked about catastrophic resurfacing. I don't like that, but there may have been something that happened 500 to a billion years ago. I can tell you about that. And, but it does look as though Venus is in a stagnant lid regime right now, but it also looks, based on the spectral admittance of the gravity and topography, that its heat flow is low. And so it may actually be cooler than the Earth. And that may be a legacy of the past evolution. It may even be heating up. If you wait around a billion years, Venus may be more exciting than it is now.
It's pretty exciting. I would have thought at the moment. Dave, we have a special SETI mug. Fortunately, due to conditions here, you can put something liquid in it and use it in the future in that manner. Please join me in thanking Dave for his great talk.
Yeah.
If you have any more questions, please feel free to come up and chat to David.